Dear students, in the last class I have discussed about maximum flow problem. In this lecture we are going to start a new topic called integer programming. The agenda for this lecture is, first I will discuss about all integer programming. After that, a special case that is called 0-1 integer programming. So, I will explain how to model and how to solve and how to interpret the result. The introduction about the linear programming is, linear programs with additional requirement that one or more variables must be integer, called integer linear programming. Many times so far we are discussing, say x1, x2, x3, these are decision variables. We assume that our constraints are non-negative, but apart from this we are going to add some integer constraint, then it will be called integer linear programming. So, this what is the meaning? This x1, x2, x3 greater than or equal to 0 and integers. Okay. So, there are three possibilities there, all integer linear programming. So, in that what will happen, all the variables x1, x2, all the variables will be the integer, must be the integer. Sometime mixed integer linear programming, some but not all variables must be integers. For example, x1, x2, x3, some variables may be integer, maybe x1 may be integers and x2, x3 may be not integer, but it is non-negative. The third case is 0-1 integer linear program. All the variables must be binary variables. Integer variables provide substantial modeling flexibility, expanding the number of applications that can be addressed with the LP methodology. So, LP methodology, there are some applications, but when you introduce integer variables, that provide a flexibility in our traditional linear programming methodology. Difficulties in solving integer programming, we have seen because of integer programming there are modeling flexibility. So, that flexibility is come with the cost also. The cost in the sense there are some difficulties. So, the cost of added modeling flexibility provided by integer programming is that the problem involving integer variables are often much more difficult to solve. Yes, there are flexibility in introducing integer programming, but it is difficult to solve. All linear programming problem with the several thousand continuous variables can be solved with any of several commercial LP solvers, but all integer linear programming problem with the fewer than 100 variables can be extremely difficult to solve. So, solving integer programming is more complex. Commercial computer packages such as Lingo, CPlex, Groby, Express MP and the commercial version of solver have extensive integer programming capability and very robust open source software packages for integer programming also available. Linear programming problem with a special structure. Because integer linear programs are harder to solve than linear program, one should not try to solve a problem as an integer program if simply rounding the linear programming solution is adequate. Some linear programming problems have a special structure which guarantees that variables will have integer values. For example, the assignment, transportation and transshipment problems have such structure. What is the meaning? In assignment, transportation and transshipment, if the variables and the cost and the coefficient of objective function everything is linear, integer, then your solution also will be integer. If the supply and the demand for transportation and transshipment problem are integer, then optimal linear programming solution will provide integer amounts shipped. So, that time you need not introduce that integer constraint, because when you bring integer constraint there is a more difficulty in solving. Now, graphical and computer solution for all integer linear programming. So, we are going to take one problem on all integer linear programming. That problem is taken from this book Anderson et al. So, that after formulating we will solve with Excel. And real estate company has $2 million available for the purchase of new rental property. After all initial screening, the company reduced the investment alternative to two alternatives to townhouses and apartment buildings. They are going for constructing two types of building, one is a townhouse, other one is apartment buildings. Each townhouse can be purchased for $282,000 and 5 hours available. Each apartment building can be purchased for $400,000 and the developer will construct as many buildings as the company wants to purchase. The company's property managers can devote up to 140 hours per month to these new properties. Each townhouse is expected to require 4 hours per month and each apartment building is expected to require 40 hours per month. The annual cash flow after deducting mortgage payments and operating expenses is estimated to be $10,000 per townhouse and $15,000 per apartment building. This will be coefficient of our objective function. The company's owner would like to determine the number of townhouse and the number of apartment building to purchase to maximize annual cash flow. There are two alternatives, one is townhouse, another one is apartment buildings. There is a restriction on amount available and there is also a restriction on number of time available for the managers. So, the problem with the manager is how many number of apartment buildings and how many number of townhouse building has to be constructed. So, we will consider the decision variable. T represents number of townhouses, A represents number of apartment buildings. See, of the objective function for cash flow in terms of 1000 is maximize Z 10,000 townhouse plus 15,000 apartment house. The fund available, so for constructing one townhouse it will take it will consume $282,000 plus $400,000 for apartment house, that should be less than or equal to $2,000 funds available. And the times when the manager can devote for townhouse 4 hours and for apartment house 40 hours, the maximum time available is 140 hours. And the requirement is there should be a minimum 5 townhouses required. So, T less than or equal to 5 and T and A is non-negative and integers. First we will solve this problem graphically. This problem I have solved with the help of Desmos. So, I have plotted all the constraints. So, the feasible region, okay, the feasible region is this region. Okay. So, when I solve graphically, the solution which I am getting 2.479 comma in x axis it is townhouse, in y axis apartment buildings. Now, when you look at this result you see that it is not integer, we are getting in terms of decimal, but constructing this decimal point and interpreting is very difficult. Now, we will go back to the presentation. Suppose that we drop the integer requirements for T and A and solve the LP relaxation of the problem. What is the meaning of LP relaxation? Initially it was integer. So, you relax that integer constraint, then you solve as usual as a simple LP problem, that is called LP relaxation. Using the graphical solution procedure, which I have solved with the help of Desmos. The optimal linear programming solution is shown in the figure. So, what is that? The T is 2.479, this value, and A is 3.252. The optimal value of the objective function is 73.574, which indicates the annual cash flow of $73,574, because all the values are in terms of 1000. Unfortunately, the real estate company cannot purchase fractional numbers of townhouses and apartment buildings. So, the further analysis required. That is why we are going to impose the integer constraints. Now, the same problem I solved with the help of solver. So, when I solve the solver, you see that the left hand side we are getting LP relaxation problem 2.47 townhouse and 3.25 apartment house. The objective function is 73.57. When I impose integer constraints, so the number of townhouses is 4, number of apartment building is 2. Now, the objective function is 70. This I will explain in solver how I got this result. Now, we solved the problem graphically. Now, I will solve with the help of solver. So, I have entered the decision variables and constraints and objective function. So, go to data, solver. So, my objective function is maximization. So, here I am not imposing integer constraint. So, it is this problem is LP relaxation problem. When I solve it, now you see the number of townhouses is 2.47, number of apartment buildings 3.25. This is a practical. So, it is impractical to implement it, because number of houses cannot be in the form of fraction, and the objective function is 73.57. The same problem I am going to impose integer constraint. Go to solver. Now, you add a new constraint, you select E5 and F5, then there is option BIN that represent INT integer, okay. Then OK, then you solve it. Yes, now this solution is which can be implemented. So, we have to go for 4 townhouses and 2 apartment buildings. The objective function is 70. Very important point, previously we got in terms of fraction, you should not round it off. So, rounding may become, the region may be infeasible. Okay. The rounding of the solution to make it integer is not recommended. The problem with rounding off, when the decision variables take on small values that have a major impact on the value of objective function or feasibility, an optimal integer solution is needed. So, when you round it off, it will not change proportionally and it become infeasible also. So, what you have to do, if in the integer in a ordinary LP relaxation problem, if you are getting solution in the form of decimal, that cannot be rounded. So, here the reduced cost, dual value and sensitivity ranges are not meaningful in integer programs. So, we cannot do sensitivity analysis, then we can do, but there is no meaning for these terms which you have seen our ordinary LP problem, like what is reduced cost, dual value, sensitivity analysis. That is why when you solve with the help of solver also, when you put an integer constraint, there will not be any option for sensitivity analysis to look. So, the application involving 0, 1 integer variables. Much of the modeling flexibility provided by integer linear programming is due to the use of 0, 1 variables. In many applications, 0, 1 variables provide selections or choices with the value of the variable equal to 1 if a corresponding activity is undertaken and equal to 0 if the corresponding activity is not undertaken. So, the value of, for example, x, this is a binary 1 comma, it can have either 1 or 0. Okay. Yeah, 1 represents the presence of this variable, 0 represents the absence of this variable. Now, we will take one sample problem, then I will introduce how to use 01 IP. This problem is taken from this book Anderson et al. The company is considering investing in several projects that have varying capital requirements over the next 4 years. Faced with the limited capital each year, the management would like to select most profitable projects. The estimated NPV, net present value, for each project, the capital requirement and the available capital for the 4-year period are shown in the table. So, this table shows the present value. There are 4 projects. What are the 4 projects? Plant expansion, warehouse expansion, new machinery or new product research. The net present value of plant expansion is $90,000, $40,000 for warehouse expansion, $10,000 for new machinery and $30,000 for new product research. Obviously, it is net present value. So, we have to choose a project, not a project, out of these 4 we have to suggest to the company what projects has to be chosen so that our net present value is maximized. Here the capital requirement for year 1 for each project is given. For example, $15,000 for plant expansion, $10,000 for warehouse expansion, again $10,000 for new machinery and $15,000 for new product research. But in the first year the capital availability is only $40,000. Similarly, the second year requirement for these 4 projects is $20,000, $15,000. There is no money required for new machinery, okay, because we are not going to buy machinery in every year. Then 10,000 and the total requirement is $50,000. Similarly, for year 3 and year 4. Now, we are going to introduce 0-1 decision variables. If P equal to 1, if the plant expansion project is accepted, 0 if rejected. W equal to 1 if the warehouse expansion project is accepted, 0 if rejected. M equal to 1 if the new machinery project is accepted, 0 if rejected. So, R equal to 1 if the new product research is accepted, 0 if rejected. Now, these decision variables are binary. Now, in the capital budgeting problem, so what we have to do? We have to maximize our NPV, net present value. We have seen previously, if you go for the first variable, that is a P, represents a plant expansion, the NPV is 90 in terms of 1000, everything is in terms of 1000, 90P plus 40W plus 10M plus 37R. The capital available in each year for year 1, right, 15P plus 10W plus 10M plus 15R less than or equal to 40. Similarly, I have written for all 4 years. Okay. Now, you see these variables are binary. Okay. Now, I am going to solve the formulated problem in Excel. So, there are 4 projects: plant expansion, warehouse expansion, new machinery and new product research. There are 4 constraints for each year. Now, go to data and solver. So, here objective function is maximizing the NPV. The changing cell is D5 to G5. Here the constraint, see, D5 to G5 is binary, that is an additional constraint which you added. Then the capital requirement constraint from H8 to H11 is less than or equal to J8 to J11. All others are as usual, only the additional constraint which you have added is binary constraint. How to add this binary constraint? So, I am selecting this binary by select that constraint. Now, go to change. Look at this, there are different options there. Select that drop down, say there is integer, binary. This is a DIF is there, that I will explain after some time. So, INT means integer, BIN means binary. So, now I am keeping it binary. So, okay. So, when I solve it, you see that one more thing, see here, since it is integer programming, in the only answer report is available, there is no sensitivity analysis. So, press OK. Now, when I looking at the result, you see I have to go for only 3 options. What are they? I have to go for plant expansion, warehouse expansion and purchase in new machinery. I should not go for new product research. So, this is an example of 0-1 integer programming. Now, we are going to consider the fixed cost. Okay. In many applications, the cost of production has 2 components. One is setup cost, okay, which is fixed cost, and a variable cost, which is directly related to production quantity. The use of 0-1 variables makes including the setup cost possible in a model for a production application. So far what we have considered in the LP models, we did not consider the fixed cost, we have considered only the variable cost. So, because of the 0-1 integer variables, we have the flexibility of considering the fixed cost, that I will explain with the help of example. The example problem is taken from this book Anderson et al. 3 raw materials are used to produce 3 products. What are the 3 products? A fuel additive, a solvent base and a carpet cleaning fluid. So, 3 decision variables are: F represents tons of fuel additive produced, S represents tons of solvent base produced, C represents tons of carpet cleaning fluid produced. The profit contributions due to these 3 products are, so $40 per ton of fuel additive, $30 per ton of the solvent base and $50 per ton of carpet cleaning fluid. Actually, the fuel additive is added along with the fuel to increase the efficiency of the fuel. We can see about the constraint. So, each ton of fuel additive is blend of 0.4 tons of material 1, 0.6 tons of material 3. Similarly, the second product called solvent base required 0.5 tons of material 1, 0.2 tons of material 2 and 0.3 tons of material 3. So, the third product for a carpet cleaning fluid required 0.6 tons of material 1 and 0.1 tons of material 2 and 0.3 tons of material 3. The maximum available of these 3 materials are, see, 20 tons are available for material 1, 5 tons of material 2 and 21 tons of material 3 are available. So, the problem for a manager is he has to determine the optimal production quantities for upcoming planning period. So, he has to suggest or he should know there are 3 products, what should be the production quantities for these 3 products. So, the objective function is maximization problem 40F, 30S, 50C. So, the constraint is 0.4F plus 0.5S plus 0.6C. Available material is 20. Similarly, for 0.2S plus 0.1C less than or equal to 5 for material 2, 0.6F plus 0.3S plus 0.3C less than or equal to 21 material 3. These are non-negative. When I solve with the help of Excel, I am getting following solution. What is that? The objective function is 1850. So, the F is 27.5, S is 0, C is 15. In this problem, we did not consider the fixed cost. In the next stage of this problem, we are going to consider fixed cost with the help of our 0-1 integer variables, binary variables. Then we are going to solve the same problem. Now, look at this, there is a fixed cost is given and the production capacity also given. What is that? The fuel additive product, that is F, okay. Setup cost, fixed cost is $200, maximum production quantity is 50. For solvent based, for second product, fixed cost is 50, maximum production quantity is 25. carpet cleaning fluid. So, the setup cost is 400 and the maximum production is 40. So, what we are going to do now? We are going to consider setup cost and the production capacity with the help of this binary integer variables. So, now I am going to introduce the binary variables. What is the SF? S means setup cost for product F equal to 1 if the fuel additive is produced, otherwise 0. SS equal to 1 setup cost for solvent base is produced. SC equal to 1 if the carpet cleaning fluid is produced, otherwise 0. So, we know from the previous table, the table which is there in the previous slide, the setup cost is 200 for fuel additive, 50 for solvent base and 400 for cleaning fluid. So, if I am going for production of this product F, I have to incur the fixed cost of 200. If I am going for production of this product solvent base, I have to incur fixed cost of 50. Similarly, if I am going for producing carpet cleaning fluid, I have to incur the fixed cost of 400. So, now I am going to consider in our objective function. Look at this, previously this component is profit, but this is cost. So, I am going to subtract revenue minus cost, that will be your profit. So, it is maximization of F. So, you have to add the minus sign because the fixed cost is the cost element, the last 3 variables cost element. The next part is, this is very interesting, to introduce capacity constraint. Okay. So, F less than equal to 50 SF. What is the meaning of this one? If the value of SF is 1, the maximum number of products on F category is only 50. If the value of SS equal to 1, the maximum production possible is only 25, that is why S less than equal to 25 SS. Okay. So, C less than equal to 40, if I am going for SC equal to 1, that means if I am opening this plant, okay, the maximum which I can produce is only 40. So, this is the best way to capture the capacity of the plant. Now, I have brought the modified linear programming problem. What is the modifications there? I have included the setup cost. Okay. These 3 was there already, but these 3 constraints are my capacity constraint. What are they? I brought in the left hand side. So, F minus SF equal to SF less than equal to 0, S minus 25 SS less than equal to 0. Here this SF, SS, SC is binary variable. Other variables like F, S, C is the non-negative variable, there is no integer constraint there. This I am going to solve with the help of solver. Now, we are going to solve the problem with the help of solver. First I have written the decision variables, for example D5, okay. D5, yes, this is my decision variables. The below that which is highlighted in yellow color is the changing cells. The objective function is highlighted in green color where the D15 is there. Similarly, below the column J I have written the resources utilized. You see that this is the resources utilized. Okay. This I am going to solve with the help of solver. Go to data, then solver. Look at this constraint first. The D15 is my objective function. This is the maximization problem. The changing variable cell is D5 to I5. Okay. This is extension. Previously I did not consider this SF, SS, SC. Now I have considered. And note that the G5 to I5 is the binary, that additional constraint is added. Then I have written all other constraint. So, when I solve it, yes, when I solve it, look at this F is 25 and SF is 1 and S equal to 20, SS equal to 1. Here the C value is 0, I am not producing any C, so I need not incur any fixed cost for SC, that is why it is 0. The value of objective function is 1350. Now we will interpret the output of our Excel. The optimal solution shows 25 tons of fuel additive and 20 tons of solvent base. The value of the objective function after deducting the setup cost is 1350. The setup cost for the fuel additive and the solvent base is 200 plus 50, 250. Because we are not going to produce the carpet fluid, so there will not be any setup cost. The optimal solution shows SC equal to 0, which indicates that the more expensive $400 setup cost for carpet cleaning fluid should be avoided. Why we are not getting SC equal to 1? Because the setup cost is high, the problem is taken care not to incur more setup cost. Okay. Previously we have considered only the profit contribution, but now in this problem we are considering the setup cost also. The problem did not consider the product which incurs higher setup cost, that is why we did not get the value for SC. So the carpet cleaning fluid is not produced. One important point in introduction of 0-1 variable for each fixed cost. The key to developing a fixed cost model is the introduction of 0-1 variable for each fixed cost and the specification of an upper bound for the corresponding production variable. This specification of upper bound represents your production capacity. So for a production quantity X, a constraint in the form X less than or equal to My can then be used to allow the production when the setup cost is Y equal to 1. So when Y equal to 1, the maximum quantity that can be produced is M. Okay. The value of maximum production quantity M should be large enough to allow for all reasonable levels of production. But research has shown that choosing value of M excessively large will slow the solution procedure. So in this lecture I have started a new topic called integer programming. I solved 3 types of problems. One is all integer programming. The second problem is 0-1 integer programming for a project selection problem. The third one is 0-1 integer problem for considering fixed cost and plant capacity. In the next lecture I will continue with the 0-1 integer problem for solving a distribution problem. Thank you very much.